you have to find yourself.
Yeah, that is find by ourselves. And actually, our approach is very lazy because we only need when we find it, we prove it, and we reload it, and we solve it.
Okay, thanks.
Yeah.
Okay, so now it is time to actually move on to the third speaker. So we see the title slide already. So yeah, go ahead.
Okay, thank you. Hi, everybody. Thank you for joining. Today, I'm going to present you our work about identifying overly restrictive matching patterns in SMT-based program verifiers. I'm Alexandra Bugariu, and this project is a joint work with Arshavir, Ter-Gabrielyan, and Peter Müller, also from ETH Zurich. So our work applies in the context of SMT-based program verification. Where given a program together to its specification, the task of the program verifier is to determine if the program is correct or not with respect to the specification. And to do so, the program verifier generates an SMT encoding of the program, the specification, and the semantics of the programming language, which usually consists of a set of axiomatizations followed by the verification condition. It then gives this SMT encoding to an SMT solver and asks if the encoding is satisfiable or not. If the encoding is unsatisfiable, the verification succeeds, and this is because technically the verification condition in the SMT encoding is negated. So if the SMT encoding holds, practically doesn't hold, practically the verification condition holds. Otherwise, from the model produced by the solver, the verifier can generate a counterexample. However, in many cases, the axiomation is actually universally quantified. So the SMT encoding is quantified, and we know that quantifier instantiation is undecidable. Therefore, the SMT solver can also return unknown, not only SAT and unsat. And this affects the verifier in two ways. It can generate incompleteness, meaning it can lead now to spurious verification errors because the verifier cannot prove that the program that fulfills its specifications is actually correct. And it can lead to undetected unsoundness in one of these axiomatizations. So the main goal of our work is to enable the developers of program verifiers to detect this kind of completeness and soundness issues, to understand the root cause and to fix them once and for all. And this can be done because the SMT encoding of various programs and their specifications are quite similar. They can share parts. For example, they can share the axiomation, or they can share the part of the verification condition that refers to the encoding of the semantics of the programming language. So as you see in this image, the three SMT encodings share the yellow axiomatization. So if the developer finds an unsoundness in this yellow axiomatization and fix it, then all the future runs of the verifier will benefit from the fix. So now let us look at a very simple example where we assume that the yellow axiomatization consists of two formulas, F0 and F1. And these formulas axiomatize the uninterpreted functions f and g. If we consider the case where x0 equals g of 7 and x1 equals 7, we see that the two formulas set contradictory constraints. Because from f0 we learn that f of g of 7 should not be 7, whereas from f1 we learn that f of g of 7 should be 7. So therefore, there does not exist any interpretation for the uninterpreted function f, such that the formulas hold, so f0 and f1 are unsatisfiable together. However, imaging, which is the algorithm that is mostly used in SMT-based program verifiers, cannot perform this reasoning automatically. And this happens because imaging is an algorithm based on patterns. These are syntactic hints, which are written here in our notation in red between curly braces. And what they do, they are written by the developers of the axiomatization, and they inform the SMT algorithm when to perform the quantifier instantiations. So if we assume, for example, that the verification condition contains, besides others, some term f of 2, which syntactically matches the pattern of the formula f0, this term is called the triggering term, then imaging will perform the instantiation x0 equals 2, and will learn from f0 that f of 2 different than 7. Without any other triggering term, no other instantiation will happen. If we now assume that the verification condition also includes the triggering term f of g of 2, which now we see that syntactically matches both patterns of f0 and f1, we will have 2 additional instantiations, and imaging will learn that f of g of 2 different than 7 and f of g of 2 equals 2. However, these 3 facts that imaging learns from these triggering terms, from these instantiations, are not enough to prove unsat. And this means that the unsoundness from the axiomatization remains undetected. What would one need is the triggering term f of g of 7 to show the unsoundness. And this is exactly what our algorithm does. Having an SMT encoding for which imaging returns unknown, our algorithm generates the necessary triggering terms that enable imaging to complete the proof. And now, having this information, knowing that f of g of 7 is the problematic case, the developer of the axiomatization can now come and fix the axiomatization by adding, for example, the precondition x0 different than g of 7 to the formula f0. Now, the key idea behind our work is that these triggering terms that we synthesize can be seen as counterexamples to the satisfiability of the input formula. And if we take an even simpler example where f0 equals for all x0, x0 greater than 7, we see that this formula is unsatisfiable. And to show that, what we can do is to generate this negation, which says exists some x0 such that x0 smaller or equal than 7. This formula is clearly satisfiable and it has infinitely many models. One possible model is, for example, x0 equals 7. If we now take this model, the value 7 from the model, and we replace x0 in the pattern that was given, we obtain f of 7, which is a triggering term, which is sufficient for imaging to complete the proof. So this is the key idea behind our algorithm, that the triggering terms that we generate can be obtained from models of formulas. Now, our algorithm contains 4 steps and assumes that the input formulas are a bit more complicated than the examples that you have seen so far, which contained only 1 or 2 formulas. It assumes there are arbitrarily many. So the first thing that it does, it clusters formulas into similarity clusters based on function symbols that they share. And the scope of this is for us to try to isolate the source of the contradiction and to explore the search space in an efficient way. Afterwards, we look at each cluster in isolation and we perform a simplified form of syntactic term unification where we identify rewritings. These are sharing constraints under which 2 formulas share terms. So for example, if we assume that f0 contains a term f of x0 and f1 contains a term f of g of x1, then through the rewriting x0 equals g of x1, both f0 and f1 share a term. And if they share terms, then they can set contradictory constraints on them. Afterwards, we generate the formula G, which characterizes the cluster. In this case, G represents the scenario in which f0 contradicts f1. And we also add the rewritings that we have identified such that the formulas are tightly connected. You can find more details in the paper how we actually obtain this G formula, but the high-level idea is that we try to make G always quantifier-free. And we want G to be encodable into first-order logic such that an SMT solver can provide a model if a model exists for this formula. Once we have the model, we construct the triggering terms as we have seen before, and we have to check if they are sufficient for the unsatisfiability proof to succeed. For this, we add them to the original axiomatization, and they are wrapped in an uninterpreted function dummy, which conveys no information about the truth value, but transforms the triggering term into a Boolean term and makes it available to imaging. If the algorithm now, if imaging can prove unsat, then the algorithm terminates because our triggering term successfully validates. Otherwise, we go back to the step of identifying candidate terms, and we repeat until we either reach a time limit or we find the suitable triggering term. So you can find more details in our paper. You can find the pseudocode of the algorithm as well as how we handle nested quantifiers. And we also have an extended version of the paper, which is available on Archive, where you can read how we handle quantifier-free formulas, formulas with multi-patterns and alternative patterns, as well as various extensions and optimizations of our algorithm that allows it to scale to real-world examples. And all of these extensions and optimizations are also illustrated on additional examples. So in terms of evaluation, we have collected benchmarks with non-triggering issues from various verifiers. We have collected unsound axiomatizations from Daphne, F-star, and Cobra, and examples with incompleteness from Viper. So in this table, we are going to show the number of benchmarks we have collected, the minimal and maximum number of formulas that they contain, the minimal maximum number of quantifiers that they contain, and in the last column for how many our work succeeded to synthesize the required triggering terms. So as it can be observed, out of 32 examples that we have collected, our algorithm succeeded for 21, including all the F-star and Cobra examples. And as it can be observed, one of the F-star benchmarks is quite large. It has over 2,000 formulas and quantifiers. And for this very large example, our synthesized triggering term is very simple. It only consists of div of 1 and 2. So this can be easily understood by the developers, and our algorithm needed roughly 60 seconds to synthesize it. Whereas if we look at the issue tracker of F-star, we will observe that for the same issue, there were needed 2 F-star developers to find out which is the source of this contradiction. So this suggests that our algorithm can automate this very time-consuming manual task. We also have additional benchmarks that we collected from SMT-com. These come from SpecSharp, from VCC Havoc, from Simplify, and the bit width independent encoding. And the table has the same structure as before. So here we can see that out of 61 benchmarks, our algorithm succeeded for 29. And it had the best performance for VCC Havoc benchmarks. These are benchmarks that are quite large, up to 1,000 formulas and quantifiers. And we see a worse performance for the bit width independent encoding. We manually looked at these examples, and what we observed is that the triggering terms that we synthesize actually trigger matching. And this is a known performance issues of the imaging-based algorithm. So now, to conclude, in this work, we have seen that the main goal of our algorithm is to help the developers of verifiers to detect completeness and soundness issues and to fix them once and for all. For this, we have proposed a novel algorithm that synthesizes triggering terms and enables imaging to complete unsatisfiability proofs. We have evaluated our work on a wide variety of benchmarks from mature program verifiers, and we have showed how it can automate a time-consuming task. And you can find more details about the algorithm, its extensions and optimizations in our paper. Thank you very much for listening, and I'm happy to take questions.
Thank you for the presentation. Are there any questions from the audience? I don't see any hand raised. And I don't see any questions in the chat. Yeah, so let me ask a question. Is there any, do you see any pointers for future work?
Yes, so one direct extension would be to try to avoid these matching loops that we have seen that are problematic. We could try by construction to generate triggering terms that don't trigger matching loops. Another direction would be, I didn't have time to talk in the presentation, but our syntactic unification is a simplified form. So what we unify are only applications of uninterpreted functions, because this can be done fast and efficiently. But one could try to extend to also support interpreted functions. And to do this efficiently, with this, we need to see how this can be done and how we can explore the third space in such a way that this will scale to real world benchmarks. And we could even try to see if we would obtain additional benefits if we would try to integrate this with an SMT solver. So our algorithm is separate, standalone, but probably if one would try to integrate it with the solver, then we will get additional benefits.
Okay, that's clear. Any questions? There is a question from Malte Schwerhoff. Nice talk, Alexandra. Regarding the examples from F*, Gobra, etc., how different are they? Could it be that all SMT encodings are from very similar source programs with similar axioms?
Not really. So all the axiomatizations that we extracted have different reasons why they are unsound. So for the Daphne and F*, we actually went through the issue tracker. We looked at the commit messages. We looked at the history and what changes have been done, and we reconstructed them manually. So these are unique errors that are there. The ones from Cobra we directly obtained from the developers, and they made sure that each of them has a unique unsoundness. So the unsoundnesses that we have considered, all of them are unique. What is more interesting is for the Viper incompleteness examples, where we collected them from the Viper repository. Then we noticed during the experiments that one could also discover some unsoundness in the underlying boogie axiomatization, which is in some cases used by Viper. And this is because these are examples of soundness modulo triggers. And you can find a discussion about this aspect in the paper. So yeah, there, I cannot say that for all the benchmarks, of all the Viper benchmarks, there is one unique issue per file, because we noticed experimentally that there can be both incompleteness and unsoundness in the same file due to the axiomatization that is included.
Okay, I hope that answers your question.